In this video, we're going to look at how to represent the Lewis structure of small charged molecules. So here we have the ammonium cation, here we have the carbonate anion. We're going to see how to represent them and then how to do the joint formal charge table and what to do about the charge on these ions. So we proceed as we did with the neutral molecules. We would identify the central atom, which in this case is nitrogen, and we surround it with the non-central atoms, and although there is no shape representation, we just try and separate everything as evenly as we can. So here I've got north, south, east and west. I connect everything once, because everything is connected at least once in a covalent species. And now I start looking at the formal charge table. Notice so far I'm ignoring the charge. So I have N, H, 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 and I put the charge alongside the elements. So it's a constituent of the species, so I write it in the constituent row. I know that nitrogen has 5 valence electrons, hydrogen has 1. I've got a plus charge. Plus charge means I've lost one of my valence electrons. So I'm going to put -1. So I've lost an electron. So whereas it looks like I have 9 electrons, I've lost 1. So I only have 8 electrons total. Each line represents 2 electrons. I should have 8 total. I have 4 lines, so I have 8 total, so there's no need to add dots. Now let's look at how many electrons are assigned. Each hydrogen is the same, so let's look at 1 to represent the whole. A hydrogen has 1 line, that's 2 electrons. You keep 50%, so half of 2 is 1. Nitrogen has 4 lines, that's 8 electrons. You keep 50%, that's 4. Top number minus the bottom number gives you the formal charge. And here we can see that nitrogen has a formal charge of +1, which must represent that charge, and we would put that on nitrogen. So nitrogen hosts, at least in Lewis theory, nitrogen hosts the positive charge. If we sum the formal charges now, this gives us +1. So this gives us the charge on the species, and we know it's a cation. We know it has a net positive charge. Let's look now at how to handle a negative charge. So look at the anion carbonate. We write the central atom, we surround it with non-central atoms, and we connect everything once. I know we have carbon, oxygen, 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 and I have 2 negative charges, so they go up here as a constituent. Carbon has 4 valence electrons, oxygen has 6. Now I've got an extra 2 negative charges, so that becomes an extra 2 electrons. So I have 6, 6, 6 plus 4 and 2, which is 24 electrons total. As it stands, I've only got 3 lines, that's 6 electrons, so I need to add another 18 electrons. Oxygen is more electronegative than carbon, which means it can pull available electrons towards itself. So let's go ahead and let's acknowledge that, and let's add electrons to complete the valence shell of oxygen. So we've got 6 dots, 12 dots, 18 dots, and then we've got 2, 4, 6 over here, so I have 24 electrons total. But whereas my 3 oxygens are isoelectronic with neon, the noble gas, my carbon only has access to 6 electrons. which means it's not quite isoelectronic with neon, which is its noble gas. Why don't we arbitrarily pick one of the oxygens, we'll take a lone pair away, and we'll replace it with a bonding pair. So again, we haven't net taken or added anything to the structure. We've just redistributed one of the oxygens, which seems to have done the trick, because now as a carbon, I have access to 8 electrons. So let's have a look. The carbon now has 4 lines. That's 8 electrons, half of which is 4. But notice now I have 2 different types of oxygen. I've got an oxygen with a double bond and oxygens with single bonds. Let's call the oxygen with the double bond A. Let's call the oxygen with the single bonds B. The oxygen with the double bond now has 2 lines, which is 4 electrons, half of which is 2. Plus you've got 4 dots, so 2 plus 4 is 6. The oxygen with the single bonds has 1 line, that's 2 electrons, half of which is 1. Plus your 6 dots gives you 7. Top number minus the bottom number gives you the formal charge. So I can see that my oxygen labeled B each have a negative charge, as indicated here. And if I sum these all up, the formal charge is up, I get my net charge for the whole species, this -2. It's negative, so I know I am looking at an anion, as expected. There is a phenomenon called resonance, which we can look at briefly here. So, in formulating this structure of carbonate, I had to change the label of the oxygen. So, for example, I had labels A and B, where originally I had no labels. So you can actually have something called resonance, which is a way to think of all the oxygens becoming the same again. So for convenience and clarity, I won't redraw the dots in this diagram. So we'll start off with our snapshot structure here. This is one of several resonance structures. If I want, I can take this negative charge on the left here, and I can dump it right onto that single bond right in the middle, which causes this double bond to break and ultimately form a negative charge here. I write reversible arrows, and I would write something like this to represent the loss of the negative charge here, the gain of the double bond here, and the loss of the double bond up here, and the gain of a negative charge at the top. So I've still got one oxygen A, and I've still got 2 oxygen Bs, but now they're in a different place. So the topmost oxygen has been oxygen A, the leftmost oxygen has been oxygen A. To complete, let's make the rightmost oxygen oxygen A. So to do that, I would have to dump these electrons in here and break this double bond again. So I could have oxygen, carbon, single bond, and then the double bond over here. And again, this can go back and forth according to this mechanism. So I could have, for example, this go back again, break this one, and then it'd be back. This is called resonance. At this point in this level of class, we'll assume that this is a way to, it adds stability. I think it's fair to say that. How does it add stability? Well, I can give you an analogy which might be useful. Imagine the negative charge is a hot coal, and so one of your friends throws a hot coal to you. It's going to hurt. It's going to give you a lot of energy if you just keep it in your hand and don't do anything with it. But if you're able to pass it to a friend, who might pass it to another friend, eventually who might pass it back, but at least some of the time you don't have it in your hand. So if you were juggling around a hot coal, either with yourself or with a friend, it would take the energy away from any one hand, just having other hands to share the burden. That's kind of a useful way, at least at this stage, to think of an analogy that would help you understand the stability that's gained by resonance. Typically, it's appropriate when asked to write a formal charge table to pick one of the resonance structures. Had we picked another resonance structure, we would have had an identical formal charge table. So it's typically accepted that when you do something like this, you've picked one of them. But it is worth at this stage being familiar with the word resonance and knowing that it adds stability.